Good morning, ladies and gentlemen. My name is Soon-Gil from Chungnam National University, Korea. Today my talk is unprecedented flexibility of in-situ layer by layer, stacked graphene with ultra-low sheet resistance. Out of my talk, so first of all, I will describe the transfer-free, large-scale, high-quality graphene synthesis on titanium buffer layer below 100 degrees C using PATCVD. Second is giant domain size of monolayer graphene was achieved at 100 degrees C. So finally, I will describe the unprecedented flexibility of monolayer and multilayer stacked graphene. So as I mentioned before, we use for titanium buffer layer for graphene growth at low temperature. So first of all, I want to describe the status of titanium buffer layer. So titanium was deposited by the DC spotter. After that, titanium take out from the chamber. So in the air ambient, titanium is very rapidly oxidized. So we check the XPS analysis like that. Titanium is naturally oxidized on exposure to air. However, so when we use the titanium buffer layer for graphene growth, so how about the stability of the titanium buffer layer in hydrogen atmosphere at the high temperature? So we check the artificial roughness change as a function of annealing temperature of different titanium buffered substrate here. As you can see, in the case of the silicon, titanium buffered silicon substrate, 900 degrees C annealed in hydrogen atmosphere, so titanium buffer layer is very stable. So from that data, we can use for the titanium buffer layer for graphene growth at low and high temperature. But in our case, we don't need a transfer of the graphene to the functional substrate. In that case, it is important to titanium buffer characteristics, so without influence of the substrate. So this is a transmittance and sheet resistance change of the titanium buffer layer with a different thickness. So in the case of the transmittance, so below 10 nanometer thickness of titanium, so transmittance is similar to the substrate and the sheet resistance. But with increasing the titanium buffer layer thickness, 20 nanometer, 30 nanometer like that, so transmittance is decreased and the sheet resistance is also decreased. From that one, so in our case, we use a 10 nanometer thickness of the titanium buffer layer. So we don't need a graphene transfer to the functional substrate. So before growing the graphene onto the titanium buffer layer, we should know that graphene grows onto the titanium layer is possible or not. So this is a simulation result. So first one is only pure titanium buffer layer, is binding energy is very low compared with the titanium oxide. So from that simulation result, so titanium should be pure without oxidation. That is very important. to grow the graphene onto the titanium buffer layer. Because of that, we fabricate the one system, titanium deposition by DC sputter. After that, we grow the graphene by a plasma assisted thermal CVD like that. So without breaking the vacuum. In this case, so as you know, the graphene is very sensitive to the plasma. So we design the plasma system like that. So substrate is apart from the plasma ambient. So in our case, we determine the 10 centimeter. So that is very important to make a damage of the graphene by a plasma. So we call the plasma assisted thermal CVD. So this one is the growth condition of the titanium deposition and graphene growth. So first of all, we should know the growth mechanism of the graphene onto the titanium buffer layer. So this is a RNS plot for determining of the activation energy of the graphene growth using the growth rate and both let's call it temperature here. So we obtain the activation energy of 0.28 electron volt. This is very low compared with the high temperature graphene growth onto the copper and nickel catalytic metal. So first of all, we want to discuss for the CVD mechanism of two different ones. This one is a mass transfer controlled mechanism. Second is a surface reaction controlled mechanism here. So this part shows a very low activation energy, and the surface reaction control mechanism have a large, high activation energy. So in our case, this is a very low activation energy, means graphene growth does not sensitive to the temperature variation. In this case, only for how much enough for a carbon supply is controlled for the graphene growth. So in our case, we want to increase the working pressure like 1.5 torr to 1.8 torr, like that. So grown graphene was analyzed by Raman, so like that. So you can see that our graphene don't have a defect, and all of graphene shows a monolayer. And then, so by a Raman mapping, so we can find out a large area graphene is possible at the low temperature of the 100 degrees C. And then, so obtain the graphene, so very high quality and no defect, and monolayer graphene is grown like that. And then I want to know how much growth temperature decrease from the 150 degrees C to 80 degrees C. As you can see, at all of temperature, so no defect, and all of graphene presented monolayer graphene, and then quality is good. So we can grow the 80 degrees C. This is makes possible for application of OLED encapsulation using the monolayer graphene. This is a very important result. So this one is a high quality by TM analysis, and we analyze the HRTM image and then Raman mapping image here using the 4-inch wafer scale of the graphene grown at 100 degrees C. So this is a very interesting result for very low sheet resistance like 78 to 83. So generally transport graphene using the high temperature growth on copper and nickel, they present a high sheet resistance of almost 500 or 600 ohm per scale. Compare with that, our graphene, so no transport, so shows a very low sheet resistance. This is a very good result. And then we wanted to check how much domain size of our graphene grown at 100 degrees C. So from that result, we determined the domain size of graphene is almost 380 micrometer on silicon substrate. Compare with that, so we repeatedly measure the domain size of graphene onto the titanium on PDMS, flexible and stretchable substrate here. In that case, every domain size is 266 micrometer. This is also very large domain size, even though graphene was grown at 100 degrees C. This is very interesting data. And then, so we want to check the mobility of our in-situ grown graphene. So we prepare the FET structure like that. So we analyze the transfer curve, so like that. So we can distinguish the single crystal graphene FET and polycrystal graphene FET. And this means that, so we already present a large domain size. And then this is a channel wide descent channel length of the FET is 20 micrometer and 10 micrometer. So this is a very small FET dimension. That means we can make this FET structure inside the domain. That is a single crystal. And then across the domain boundary, that is a polycrystal FET. So we can separately prepare the FET structure, single crystal and polycrystal like that. So in the case of single crystal FET, we obtain the high hole mobility of 40,000 square centimeter per second. This is a very large hole mobility. So last one, we wanted to, how can we decrease the sheet resistance from the 70 or 80 ohm per scale? So there are so many reported data for multilayer stacking for decreasing the sheet resistance. So all of them are a solution technique and a very complicated process here. But in our case, we can in-situ multilayer stacked is possible. So one layer graphene titanium pad, 2 layer graphene TI pad like that. So we prepare the 4 layer stack in this case. So we measure the sheet resistance as a function of graphene layers. So at 1 layer shows 80 ohm per scale. But with increasing the graphene layers, so at the 4 layer stack, so 6 ohm per scale is possible. And then transmittance is slightly decreased of every stack 2.2%, like that. So this is a very important data. But why? Why this sheet resistance is left decrease with increasing the layers? So you can see that the FET structure with multi-layer stack. In this case, 1 layer and 2 layer and 3 layer and 4 layer stacking, and then so Dirac voltage is positively shifted like that. This means so when we grow the 1 layer and the 2nd layer, third layer, In-Situ, after that take out the air ambient, so oxygen is diffusion into the layer in the air. So that is p-doping. So like that, our graphene, stacked graphene is naturally so prepared of p-doping. So, but this is a very stable at the high temperature and high vacuum state annealing. This is not change. So from that region, so we can obtain the very low sheet resistance of 6 ohm per scale at the 4 layer stacking. So from this result, we want to describe the flexibility. So this one is reported data in Nature Nanotechnology using the transport graphene onto the pad. And you can see that this is a graphene, and then this is an inset figure. So compressive is stable, but tensile case, so only 1% bending, strain, and then resistance is rapidly increased. But this one is our graphene is also transport on PDMS. So this data, and this is a reported data. So compare with that. So some different flexibility depends on the substrate. So I want to show that. But in our case, so our data is a single layer, 2 layer, 3 layer onto the PAT substrate. So 7% tensile strain, so like a normalized sheet resistance change is 10% below, like that. But with increasing the stacking layer, some flexibility increase, like that. So from that one, we can describe the cycling number, like that. So single layer, 2, 3 layer stacked here. So this is a 10,000 cycle bending, and then below 10% is stable at 5% tensile strain. But so first of all, I want to check the flexibility of graphene by the substrate. This is a PET substrate only. So this is a bending strain here at 11% tensile strain. After that, so force is removed, and then PET substrate is not recovered, like that. This is a bend state. This is a very interesting for influence on the graphene's flexibility. So next one is we check the PDMS PAT substrate and the PDMS substrate here. So PDMS substrate, PAT substrate here, this is only 5% is recovered, but above the 5% that is not fully recovered here. But PDMS substrate case, so all of the tensile strain that is completely recovered. So this is very important for influence of the graphene flexibility of different substrate. So first one is a PDMS PAT substrate. In this case, a little bit increase of the tensile strain compared with the only PAT substrate. This is a tensile strain. So this one, you can see that below 10% normalized resistance is almost 11%. So you can see that the almost 50,000 cycle number is stable at 9% and 7% tensile strain. But in this case, so single layer graphene on PDMS at 15% strain is very stable, like that. From this data, we wanted to conclude we may grow the transfer-free graphene high quality, large size, and right domain size at 100 degrees C. This is a very high flexibility, and multilayer graphene more highest flexibility than that of monolayer graphene. Thank you very much.